Welcome to the video on radical reactions. An introduction to radicals. Up until now, we've talked about doing polar reactions, where we take two electrons and we use an arrow and we move those two electrons. That is called heterolytic bond cleavage and bond formation. Radical reactions are homolytic. So if we have a bond shown here with two electrons, radical reactions, each electron goes one way. And so we have homolytic cleavage. And we end up with single electrons. So we have a single electron on the X and a single electron on the Y. And those are considered radicals. Up until now, we have used a double barbed arrow to indicate that we had two electrons moving. For radical reactions, we use what's called a fishhook arrow, meaning that only a single electron moves. What does a radical look like in terms of structure? Remember a carbocation, we had that empty p orbital, and the three groups that were attached to our carbon were planar. And with a carbanion, because those two electrons occupy an sp3 hybridized orbital, that shape is tetrahedral. For a radical, because we have a single electron, we can think about it one of two ways. We can think about it as being strictly trigonal planar, where we have the p orbitals not quite empty, but it acts empty. Or we can think about it where it very quickly interconverts between a very shallow pyramid and then the inverse of that pyramid. If we talk about free radical stability, it is the same as carbocation. Now, radicals do not have a formal charge, but they're still electron deficient and they have an incomplete octet. They follow the same trends as carbocations. Bond strength is therefore inversely proportional to the carbon radical stability. The more stable of a radical we create, the weaker that bond was. And so we see here methyl, and then more stable is primary, then secondary, then tertiary, just like carbocations. And we can also see here that CH bond right there is going to be stronger than the CH bond here, and that is because this radical product is more stable, and so that's a weaker bond. Radical species can exhibit resonance. If we have an allylic radical right here, we can, remember using our fishhook arrows, kick that in, and then one of these two electrons comes over here, and then that last electron hops on the end, and so here is the resonance structure. And the same with benzylic radicals. We can move that radical right around the ring, just like we did with carbocation resonance structures. Resonance plays a bigger role in radical stability in terms of resonance than primary, secondary, tertiary. If we have a tertiary, that bond energy is 381. Allylic, the energy is 364. And benzylic, the energy is 356. And so as that energy decreases, it means it's a weaker bond. It means the more stable benzylic radical comes from that weaker bond being broken. Notice that vinylic is very high energy, so that is a very strong bond, and that means that radical would not be stable. Same with a primary. That bond is very strong, and so the radical is not very stable. You may remember learning the patterns that were possible for polar or ionic mechanisms. In this chapter, we're going to learn those patterns that are possible for radical mechanisms. Radical mechanisms are distinctly different. For example, radicals do not undergo rearrangement, and that should be a good thing, right? So we don't have to worry about rearrangement when we have radicals. We do have 6 key arrow pushing patterns for radicals. And here are the 6. We can have homolytic cleavage, and this needs to be initiated by heat or light. And that's where we have the 2 electrons in the bond. One goes each way, and we're cleaving that bond, and we're making 2 radicals. We can have addition to a pi bond, and so that single electron reacts with one of the electrons from the pi bond to form a new sigma bond right here, and then we have that last electron hop onto the end, and so we end up with this product. We can have hydrogen abstraction. Now, this is not a proton transfer because we're bringing one of the electrons with it. Proton transfer is just the hydrogen without any electrons. Remember, hydride is with both electrons. So this is hydrogen abstraction. So if we have 2 electrons in this bond right here, and then there's our radical there. So what happens is one of these electrons and this go together to form a new sigma bond, and then that last one hops on. So our R is radical, and now we have H and X bound. Halogen abstraction. So we again have our radical here, and we have our 2 electrons in that bond. So this electron plus one of the bonding electrons forms a new sigma bond here, and then that electron hops onto the X, and we're left with this new RX bond and X radical. Or we can have elimination, where we have a radical that's on a carbon that is alpha to a good leaving group, and so we have that electron kick in, and then we have one of the electrons from this bond kick in, so we create a double bond, and then that last electron hops on the X as the leaving group. So we end up with a leaving group, radical, and an alkene. And finally, coupling. And coupling is when we have 2 radical species come together to form a new sigma bond. And so that is actually the opposite of the cleavage, which is in pattern 1. So we create now a new sigma bond from 2 radicals. So it turns out that these 6 patterns are actually only 3 patterns, which are in the forward and reverse. The most obvious one is homolytic cleavage, where we take a sigma bond and homolytically cleave it to create the 2 radicals, versus the reverse of that, we have coupling, where these 2 come together to form the sigma bond. We can have addition to a double bond, or we can have elimination, creating a double bond. And finally, we can have hydrogen abstraction, where we have some carbon group with an H that adds the X, or we can have a misprint there that should be halogen. We can remove the halogen and replace it with an H. So we can either take off a hydrogen to make an alkyl halide, or we can take off a halogen to make an alkane. Now, one more thing we have to know about radical reactions are the 3 steps that are involved in radical mechanisms. This is different than the patterns, although you can see some similarities. Initiation, termination, and propagation. The initiation step is first, and that is where we form the radical species. So we have some sigma bond between 2 atoms, and we do homolytic cleavage to create 2 radicals that can then go on and continue reacting. That's the initiation step. Propagation, I think of the Energizer Bunny. This is where we have a radical, we react with something, and our product is still a radical. So it just keeps going. So if we add to a double bond with our radical, we still have a radical in the product. If we do hydrogen abstraction, we still have a radical in our product. If we do halogen abstraction, we still have a radical in our product. And finally, if we do elimination, we still have a radical in our product. And so this is called propagation. And propagation is where we have a radical, we do a reaction, and we still have a radical, which differs from the last step, which is called termination. And termination is where we have 2 radical species that come together and quench that radical reaction. So we pull those together, we make a sigma bond, and we do not continue the radical reaction. This is now quenched. If we show now an example, the chlorination of methane, and we walk through our initiation, propagation, and termination steps, we can see if we have methane and we react it with Cl2 in UV light, we can add a chlorine to our methane. So in the initiation step, we have homolytic cleavage. We need UV light, and we make 2 chlorine radicals. In our propagation step, that chlorine radical can abstract a hydrogen. So we're going to kick that radical electron in, 1 from that bond, we'll make a new bond here, and then that kicks up. So we end up creating a new radical and having HCl as a product as well. We can also do halogen extraction, in which case we can now take this radical from that first propagation step. Now that becomes our reagent, and we actually react that with one of the electrons from that bond right there to make a new sigma bond here. And then we have this electron kick up on. So we end up with a new alkyl halide and our chlorine radical. So again, in this step, we start with a radical, we end with a different radical. And now termination of this step, we can have a couple different things come together. Remember, anytime we've created a radical, that radical may still be around. So we can couple together 2 chlorine radicals to recreate our Cl2 we had as our reagent. We can couple a chlorine radical with a methyl radical to create now our alkyl halide, or we can couple together 2 of our methyl radicals, kick those both in to create a new bond here, making ethane. So I hope that this example shows you that there can be a lot of different products formed. Radical reactions are actually pretty difficult to control. Once we get that radical formed, it kind of can go on and do whatever it wants. And I haven't even mentioned yet that very often we can have multiple chlorines add. So when we're doing the chlorination of methane, we can have multiple chlorines add. And it turns out we can have one, we can have two, we can have three, and we can actually have four attached. It turns out that methyl chloride is more reactive than regular methane to radical reactions. So it just kind of propagates through it, end up getting multiple halogenations. If your desired product was the monochlorination, then we'd want to use an excess of methane. How do we get this all going? Well, it turns out we need initiators. So radical initiators possess a very weak bond that cleaves homolytically with light or heat. Dihalides are a great example. Peroxides are a great example, and this acyl peroxide as well. And those are three very common species that are used to get radical reactions going. Once we get to compounds that are more complex than methane or ethane, we can actually have different monohalogenation products. For example, if we have propane 3-carbon chain, we have the primary hydrogens that are shown in green here, and there's 6 of those. And then we have 2 secondary hydrogens. So we could get 2 different products. We can replace one of these hydrogens to get this product, or we can replace one of these hydrogens to get this product. Now, chlorine is pretty indiscriminate. In other words, we really get a mixture of both of these products with chlorine. It's not regioselective at all. But if you think about it, those secondary radicals were more stable than the primary, right? So the secondary halide should be the major product. And here's the energy diagram. The secondary radical is more stable. The transition state energy is lower as well. So the activation energy is lower. So that secondary radical will form faster. And so we see that as our major product. Bromination, on the other hand, is much slower. So there's much more opportunity for it to be selective. Bromine is much more selective for that more stable secondary carbon radical. So bromination is much more regioselective, and it can be explained by the Hammond postulate. If we focus on that rate determining step, which is the hydrogen abstraction, we can see that the transition states for the chlorine versus the bromine look very different. In terms of the chlorine, the hydrogen carbon bond is only beginning to break, whereas with the bromine, that bond is almost completely broken. And so if we look at that in terms of energy diagrams, the reactants are much closer to the transition state in the chlorine example, whereas the intermediates are much closer to the transition state in the case of the bromine. So bromine is much more regioselective. For bromination, the stability of the transition state largely depends on the resulting carbon radical stability. Whereas for chlorine, the stability of the transition state does not depend at all on the resulting carbon radical. So if we pull this all together, we can see with chlorine here, the differences in energy of the transition state are not that pronounced. And so there's going to be less selectivity. Whereas in this case with the bromine, the differences in the transition state energy and the activation energy are substantial. We're going to very much prefer that lower energy of activation, lower transition state energy of the tertiary radical over the secondary and the primary. For bromine, that tertiary position is 1,600 times more reactive than the primary position. And here's a table describing those reactivities. Sometimes radical reactions can create stereocenters. We will get a racemic mixture. Remember that radical intermediate is mostly planar, so we can attack from both sides. So whether we call it trigonal planar or we call it a rapidly interconverting shallow pyramid, either one of those, we're going to get reactions from both sides. So when we have butane and we do chlorination of butane in a radical mechanism, we get a racemic mixture of the two where we replace the secondary hydrogen, and then we get a third product where we replace one of the primary hydrogens. If we have halogenation of a compound that is already chiral, we will get a racemic mixture. And remember, with bromine, that tertiary carbon is going to be the one that reacts. That's going to be the one that creates the most stable radical, and that's going to be the weakest CH bond to break. There you have it. Radical reactions, an introduction.